Hello class, and welcome to our next video lesson on atomic bonding. We're going to talk a lot in this video about how atoms bond because atoms don't typically exist in nature alone. They like to bond with other atoms to form compounds and molecules, which is what we're going to get into in this lesson. But before we get to that, let us first review what we've already learned about atomic structure. We have learned that at the center of every atom there is a nucleus, and within that nucleus you have your protons and your neutrons. Outside of the nucleus, you have some empty space, and this is where your electrons exist. The electrons, they travel around in an area that we call the electron cloud. This is where your electrons are, and then your protons or neutrons are right here in the center, which is what we call the nucleus. Protons and electrons have a charge, and this charge will help determine the charge of an atom. Protons are positive and the electrons are negative. The neutrons don't have a charge, so they don't really have anything to do with the charge of the atom. A neutral atom will have the same amount of protons and electrons, as we can see here in this picture of a neutral lithium atom. You've got the same number of electrons and protons, therefore they cancel each other out, and this is what you would call a neutral atom. Now, let's talk more about the electrons and their arrangement, because what we're going to learn in a few slides from now is that the electrons have a lot to do with the bonding of the atoms. But let's talk about the electron levels, the energy levels that the electrons live on. The different areas for an electron in an atom are called energy levels, and each one of these energy levels is going to have a different amount of energy. Therefore, they're going to hold a certain number of electrons. We've learned from last week's lesson that the first level is full with 2 electrons, and then the second and third levels are full with 8 electrons. Electrons that are closer to the nucleus have a lower amount of energy, and they're said to be at energy level 1. Now, as you get further away from the nucleus, those electrons are going to have a higher amount of energy and be a little bit more excited, and that's why it's going to be very easy to remove these electrons from the atom when bonding occurs. We just learned a few slides up that protons are positive. So the center of your atom, the nucleus, is going to be positively charged. Electrons are negative, and we know the old saying that opposites attract. So the positively charged nucleus is going to be strongly attracted to the negatively charged electron. Therefore, electrons that are closer to the nucleus are going to be harder to pull away, or it's not going to be that easy to get them off of the atom, versus ones that are a little bit further away from the nucleus. It's going to be easier to remove them because that attraction is not as strong as you get further away from the nucleus. So therefore, removing electrons that are close to the nucleus takes more energy than removing those that are further away from the nucleus. Now, let's talk more about what we learned about the periodic table and energy levels, because the periodic table, the way that it is arranged, it gives us a lot of information about these atoms and elements, and there are certain trends that they follow, which is kind of how the table was organized in the first place. There are several trends and patterns that you will notice about electrons and energy levels on the periodic table. Let's look at this periodic table here, which shows you some atomic models, and it shows you the distribution of their electrons on the energy levels. It says, what trend do you notice about the energy levels for elements as you move down a group? Well, we know that a group on the periodic table is the same thing as a column. So let's look at hydrogen, lithium, and sodium. You will notice that as you move down a group, you can see that your energy levels, or the number of energy levels, is starting to increase. Hydrogen only has 1, lithium has 2, sodium has 3, and then if we were to go further down, we would see the increase in these energy levels as you move down a group. Let's look at another trend that you may notice. What trend do you notice about valence electrons? And valence electrons, like we learned in last week's activity, are electrons on the outermost energy level as you move down a group. So let's look at that same group again, hydrogen, lithium, sodium. And what do we notice about the number of valence electrons as you move down a group? If we look in this first group here, you will notice that all of these elements only have 1 valence electron in their outermost energy level. Well, let's look at group 2, beryllium and magnesium. How many electrons do you see in that outermost energy level? If you said 2, then you are correct. So as you move down a group, there are certain trends that you're going to see. We see an increase in the number of energy levels. We also see that there is a consistently the same number of valence electrons on the outer on that outermost energy level as you move down a group. And you can see that pattern as you go, if you go down each group that's seen here on the periodic table, you can see that trend. Now, what I do want you to pay attention to is look at group 18. Now, group 18, this is a group where the outermost energy level is considered to be full. So, although the number of electrons here is not the same as here, this group here, is the most stable family of elements on the table. Helium has 2, but that's considered full. So instead of you saying, well, they have the same number of valence electrons, you can see here that all of these elements have a full outer level. All the outer levels are considered full. Now, let's look at one more trend before we leave this slide. What do you notice about valence electrons as you move across a period? So let's go across a period. Let's go across period 2. Lithium has 1 valence electron, beryllium has 2, boron has 3, carbon has 4, and so forth and so forth. As you can see, as you go across a period, the number of valence electrons increases by 1. As you go across the period. So just to kind of sum up what we see here, there are several trends and patterns that you will notice about the electrons and the energy levels on the periodic table. All right, let's look at some periodic table families because this is something that you looked at in your activity last week. Just as human family members often have similar looks and traits, members of element families have similar chemical properties because they have the same number of electrons in their outer energy levels. And that's what we learned when we first introduced the periodic table. We talked about how the periodic table was organized according to what these elements have in common. So let's look at a few families here on this table. The noble gas family, that's the family that's in group 18 that I was just talking about on the previous slide. It is 8 electrons in the outermost energy level for most of them except for helium. But what we would say is that these are stable atoms and that their outermost energy level is full. They do not combine easily with other elements because they're pretty much happy. They have a full outer level, which is kind of what all other atoms are trying to do, is get a full outer level so that they're kind of be at a more of a stable be in a more stable condition. So these elements are ones that typically you would find kind of coexisting by themselves in nature. They don't tend to bond with other elements because they already have a full outer level, which is what atoms are trying to achieve through bonding. Let's see, let's look at the halogens. The halogens are considered group 17 on the periodic table. The reactivity of the halogens will decrease as you move down a group. As the outer energy levels, they get further away from the nucleus. Fluorine, which is at the top of the family, is going to be the most reactive halogen, and halogens will tend to have 1 valence electron. No, let's make a correction there. Halogens tend to have 7 valence electrons. Okay, that's an error there on the slide. They have 7 valence electrons. So a lot of times halogens are looking for an atom that they can get another electron from so that they can have that full level of 8. So typically halogens are going to gain an electron, and we're going to talk about that in just a minute. What does that mean to gain an electron? All right, let's look at the alkali metals. Now, alkali metals are also, they're very reactive. Unlike halogens, however, the reactivities of alkali metals will increase down the group instead of decreasing. These are the ones that have 1 valence electron in their outermost energy level. So these two groups are pretty reactive groups, halogens and your alkali metals. Halogens, of course, are nonmetals, and then your alkali metals are metals, but they're both very reactive families from the periodic table. Now, let's talk about the electron dot diagrams because this is a handy way that we'll use to kind of figure out and look at how these atoms are bonding. If you want to see how atoms of one element will react, it is handy to have an easier way to represent the atoms and the electrons and their outer energy levels. We use what is called an electron dot diagram, which is also called a Lewis structure. An electron dot diagram is the symbol for the element surrounded by as many dots as there are valence electrons. And once again, those are your electrons in the outermost energy level. Let's look at an example of an electron dot diagram. The dots are written in pairs on four sides of the element symbol. You start by writing one dot at the top of the element, then you work your way around adding dots to the right, bottom, and left. So let's look at nitrogen. Nitrogen has 5 valence electrons. Remember, that's the electrons in its outermost energy level. So we would start by putting a dot here, 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 and here. That gives us 4 dots. And then we would put another one right here to kind of pair that one up. So that gives us a total of 5. Let's practice with an element. Let's look at iodine. So let's draw the symbol for iodine, which is a capital I. Now, iodine is found in group 17 on the periodic table. So it's the atoms in that particular group, they're going to have 7 valence electrons in their outermost energy level. So let's go ahead and put some dots around this diagram to represent that. And I'm going to start by just doing one dot here, 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 and here. Okay, so now I have one on all 4 sides, but that's not enough. So now I'm going to come back and kind of pair some of them up. So that gives me one right here, then one here, and then one right here. So now I have made a electron dot diagram for iodine. And remember, what you'll show, the dots around the diagram, or around the symbol, excuse me, show the number of valence electrons, okay? And we're going to use this to kind of show how atoms bond together. All right, now that you know how to write electron dot diagrams for elements, we can use them to show how atoms bond with each other. A chemical bond is the force that holds 2 atoms together. Atoms bond with other atoms in such a way that each atom becomes more stable. Remember, I said earlier that all atoms are trying to achieve stability. And in order to do that, they're trying to get their outermost energy levels to be full. Okay? That is, their outer energy levels will resemble those of the noble gases. Noble gases is group 18 on the periodic table. Those are the group of elements that have a full outer energy level. So all elements are trying to achieve that for stability. Let's talk about the different types of bonds. Atoms form bonds with other atoms using electrons in their outer energy levels, which is what we just discussed. There are 4 ways to do this. You can lose electrons, gain electrons, pooling electrons, or sharing electrons. Now, the ones that we're going to focus on for the rest of this lesson are losing electrons, gaining, or sharing. Those are the 3 that we're going to talk about in the rest of the lesson. Let's talk about ionic bonds, because this is how, when bonding occurs, you can have a loss or a gain of electrons. Let's talk about sodium. Sodium has only 1 electron in its outermost energy level. So it would be much easier for sodium to kind of get rid of this 1 electron instead of trying to gain more. So typically, sodium will lose that outer energy level, that outer electron. Removing this electron will empty that level, and that leaves the completed level below. So look at the picture. Once sodium kind of loses that outer electron to another atom that it bonds with, then that gives sodium its stability, which is what it's looking for. It's wanting to have that outer level to be full. So by removing 1 electron, sodium's becomes the same as that of a stable noble gas neon, which is what they want. Atoms want stability. So sodium will typically lose 1 of its electrons, and if it does that, it's going to make sodium more positive, because now sodium has more protons than it does electrons. Okay, so now that's going to give sodium a +1 charge. All right. Now let's talk about the flip side of that. What if the atom gains an electron? Chlorine forms bonds in a way that it is the opposite of sodium. It will gain an electron. When chlorine accepts an electron, its electron becomes the same as that of the noble gas argon. So chlorine is an atom. It already has 7 valence electrons out here. Okay, and I'm looking at the ones on this outermost level. So chlorine kind of likes to gain an electron, therefore making its outer level more stable. When it does that, then it has stability. It has 8 electrons out there, which is what it wants to do. So chlorine, since it is gaining an electron, it's going to become more negative because now it has more electrons than it does protons. So now the atom takes on more of a negative charge. Chlorine actually has a -1 charge to it. Okay? So, by losing an electron, the balance of electric charge changes. Sodium becomes a positively charged ion, which is what we said in the previous slide, because there is now one fewer electron than there are protons. An atom that is no longer neutral because it has lost or gained an electron is called an ion. And we did talk about this word in our previous video lesson. So when atoms gain or lose electrons, they then become ions. And that's what happens when they're bonding. All right, so let's look at a full bond formation here. The positive sodium ion and the negative chloride ion are strongly attracted to each other because sodium is trying to get rid of its one electron out there, and chlorine is trying to gain one to make its outer level full. This attraction, which holds the ions close, is a type of chemical bond that we call an ionic bond. Ionic bonds happen when atoms gain or lose electrons. It's kind of like the transfer of electrons whenever ionic bonding is occurring. Typically, ionic bonds are going to happen between a metal and a nonmetal. And if you look at your periodic table, you will see that sodium is a metal and chlorine is a nonmetal. So that's typically what happens with ionic bonds. They happen between metals and nonmetals. All right. The compound sodium chloride or table salt is then formed. Whenever sodium and chlorine come together, then you get what is called sodium chloride. A compound is what is formed. It's a pure substance containing two or more elements that are now chemically bonded. And down here we can see an example of what happens with the Lewis dot structures. Sodium only has one outer valence electron. Chlorine has 7. And then when they form their ions, sodium gets rid of that one um, electron that it had. Let's see if we can see this. So what you have here is you get a transfer of this electron. It kind of goes over here. So then what we end up with is sodium has lost its electron, so it becomes more positive. Chlorine has gained an electron, so it becomes more negative. All right, and that just kind of shows you what happens with the electron dot diagrams. Can elements lose or gain more than one electron? Yes, they can. The element magnesium, which is located in group 2, has 2 electrons in its outer energy level. So it's easier for it to get rid of those 2, and then once those 2 are gone, it can have that full outer level that it's seeking. Magnesium can lose 2 electrons and then achieve a completed energy level. And this is typically what what elements in group 2 will do. They will lose those 2 valence electrons. And as you can see right here, oxygen is an element that has 6 valence electrons. So in order for it to achieve stability, it wants to have 8. So it's easier for it to take those 2 from magnesium, and then these can bond, and they will form what is called magnesium oxide. So yes, elements can lose or gain more than one electron. All right, let's switch gears here and talk about covalent bonding, which is the sharing of electrons. And this is misspelled here. I'm going to scratch that out. This is called a covalent bond. Some atoms are unlikely to lose or gain electrons because the number of electrons in their outer levels, makes this difficult. The alternative is sharing electrons. So not all atoms are going to lose or gain because sometimes it's just hard to do that depending on how many electrons they have in their outer levels. So they'll do the alternative, which is to share the electrons instead. The covalent bond is a chemical bond that forms between nonmetal atoms when they share electrons. Covalent bonds happen typically between 2 nonmetals, okay? Remember we said ionic bonds happen between a metal and a nonmetal. Typically with covalent bonds, that's going to be between 2 nonmetals. And you can see right here, these are 2 oxygen atoms that have come together, and they are sharing these electrons here. Okay, they oxygen has 6 valence electrons. So what they do is they share these electrons here, and then that gives both of these atoms a full outer energy level. They're more stable. Shared electrons are attracted to the nuclei of both atoms. They kind of move back and forth between the outer energy levels of each atom in the covalent bond. So each atom has a stable outer energy level some of the time. The neutral particle that's formed is when atoms share is called a molecule. And you can kind of see some examples here. You've got 2 hydrogen atoms that come together and they're sharing those 2 electrons. And then you have 2 chlorine atoms that come together and then they're sharing some electrons as well. An atom can also form a covalent bond by sharing 2 or 3 electrons. When 2 pairs of electrons are shared by 2 atoms, the bond is called a triple bond. And we can see an example of that here. You've got one carbon atom coming together with 2 oxygen atoms. And right here, they're sharing pairs of electrons between the oxygen and carbon on this side and then the oxygen and carbon over here. So this right here would be considered a double bond. This would be a double bond between those atoms. You can also form a triple bond. When 3 pairs of electrons are shared by 2 atoms, the bond is called a triple bond. Each nitrogen atom shares 3 electrons in forming a triple bond. So when 2 nitrogen atoms come together, they are sharing these 3 pairs of electrons here, and this would be called a triple bond. That is what we would call a triple bond. Chemical shorthand. All right, now that let's kind of just take a moment and think about what we've learned. We've learned about ionic bonds formed when atoms are losing or gaining electrons, and covalent bonds formed when atoms are sharing electrons. Now we're going to talk a little bit about how we kind of write out these formulas for these different bonded atoms when they have formed together. Alchemists use elaborate symbols to describe elements and processes. Modern chemical symbols are letters that can be understood all over the world. So that's why we use chemical shorthand to represent these atoms once they've bonded together, because it's kind of a language that we can all understand, no matter where we're from in the world. Each element is represented by a 1-letter, 2-letter, or 3-letter symbol. Many symbols are the first letters of the element's name, such as H for hydrogen or C for carbon. Others are the first letters of the element's name in another language. Compounds can be described using element symbols and numbers. For example, 2 hydrogen atoms join together in a covalent bond. The resulting hydrogen molecule is represented by the symbol H2. The small 2 after the H in the formula is what we would call a subscript. That's the 2 here that you see. The subscript just really tells you how many atoms of that element are making up that molecule. That's what the subscript will tell you. A chemical formula is a combination of chemical symbols and numbers that show which elements are present in a compound and how many atoms of each element are present. When no subscript is shown, the number of atoms is understood to be 1. A water molecule contains 1 oxygen atom and 2 hydrogen atoms, so its formula is H2O. So 2 hydrogen, you have a 2 beside the H, which tells you how many hydrogen atoms, and then oxygen is only 1. And you never write the 1 in a chemical formula, it's just always understood to be 1. How would you write the chemical formula for the compound sodium chloride? 1 atom of sodium and 1 atom of chlorine. Hint: when writing the chemical formula for ionic bonded atoms, the metal is written first in the formula and the nonmetal is written second. So for this one, sodium, which is abbreviated with N lowercase a, and then chlorine, capital C lowercase l, is how you would write the formula for sodium chloride, which is the same thing as table salt. And since there's only 1 atom of each in this particular compound, it's just understood to be there. So this is 1 sodium atom and 1 chlorine atom. That brings us to the end of our video lesson on atomic bonding. Make sure that you have adequate notes taken in your notebook. Make sure that you have followed the outline and checked off all of the things that you should have had notes on for this particular video lesson.